Hello, this will be an introduction to the transition from two-dimensional integrals to three-dimensional integrals. For this, suggested intro activity is to begin by graphing y equals 9 minus x squared on Desmos, and then consider the meaning of the integral from -2 to 2 of 9 minus x squared dx to the graph of y equals 9 minus x squared. Then consider what the graph of z equals 9 minus x squared minus y squared looks like on GeoGebra. And then think about what the meaning might be for an integral of that graph. So if we think about it, so the graph of y equals 9 minus x squared is a parabola. It's an upside down parabola. The integral from -2 to 2 of 9 minus x squared is the area underneath that parabola between x equals -2 and x equals 2. Now, if we consider the graph of z equals 9 minus x squared minus y squared, that ends up being sort of an inverted cone. Really, it's an inverted paraboloid. However, it has the general shape of a cone. Now, if we consider the integral under a cone, instead of being area, this ends up being volume. And this brings us to the idea of a double integral, meaning an integral in three dimensions. If we look at a function of two variables, a function of two variables forms what's called a surface, which ends up being almost like you took a piece of paper and made a shape and you put it on top of a table. That surface encloses a volume. And so a double integral, which we need two integrals because we have two variables that we're integrating for, that double integral will tell you the volume underneath that surface. Now, if we look at single integrals, consider what shape we used to approximate them. For single integrals, we use rectangles. Now, if we extend rectangles by one dimension, we get what in common language would be a box. Really, it's a rectangular prism. However, a box is much more intuitive. And so we can use this concept of boxes to approximate a double integral by finding the volume over a certain width and length. And it looks kind of like this. So what we're doing here is we're taking the width of the base, the length of the base, and then this function is the height of the base. So this function goes up and down right here. This width goes in one direction, and then the length goes in the other direction. And we're doing that for boxes spaced at either equal intervals or different intervals, but either way, we're splitting up the surface into these boxes, which we can calculate because it's just a reasonable geometric formula, and then we're taking the sum. So remember, these sigma signs mean we're summing these boxes. So an example of this using boxes to approximate areas is if we take the double integral of x squared plus y cubed over the region from 0 to 1 on x and 0 to 3 on y. So doing this, we're going to end up with different boxes. So we're going to end up with one box here that is the region from 0 to 0.5 on x and 0 to 1 on y. So the width is 0.5, the length is 1. And we're going to use the left corner. So the left corner is x is 0, y is 0. So this is volume 0. Then we're going to move over. We're going to do the box from 0.5 to 1 for x and from 1 to 2 for y, or actually from 0 to 1 for y still. The height of this is going to be the left corner. So 0.5 for x, 0 for y, because what we're doing, we can think of this as we take the region from 0 to 1 and we split it in half, and we take the region from 0 to 3, and we're just going to take by 1 here. So this is y is 1, this is x is 0.5, and so our first box is right here, then our next box is right here. So that is from 0.5 to 1 on x and from 0 to 1 on y. And then we move up to this box right here, which is from y equals 1 to y equals 2 and x equals 0.5 to x equals 1. And we keep going like this. So it's just a process of, for each of these boxes, so for each of these boxes, we're going to calculate the volume of it, and then we're going to move on to the next box. So we've got 6 of these in total, and from estimating it based off these boxes, we'll get an approximation of the double integral. Please note that even for something that is just 1 wide and 3 tall for a relatively simple function, this is how much work we have to do. So this approximation method, yes, you can do it. However, honestly, it's kind of a pain. And in case you're wondering, yes, there is a better way, and we are going to do the better way for most of the time. So an example of how to calculate double integrals effectively instead of approximating them is the idea of we take the integral with respect to one variable, and then we take the integral with respect to the other variable. What order we do this does not matter so long as the function is continuous, and really we're not going to run into many functions where the order of integration cannot be switched. So for our example, we're going to take the same function we had before, x squared plus y cubed, and we're going to integrate it on a similar region. We're going to go from 0 to 2 with respect to x and 0 to 3 with respect to y. So the first thing to do is to write it as what's called an iterated integral, meaning we've got two different integrals with limits that are stacked inside of each other. Now, a key thing to note is that the variable inside has to match the limits that are inside. So we have 0 to 3 for y, and our inside integral is dy with 0 to 3. So that's matched up. And then the outside is going to be the other variable. So in this case, dx, and it's matched up with 0 to 2. So that's the first step, is to write it that way. The next step is we're going to take an antiderivative with what's the variable that's inside. So we've got dy inside. So we take an antiderivative with respect to y. And so the antiderivative of x squared with respect to y is x squared y. The antiderivative of y to the third is 1/4 y to the fourth. And we'll be evaluating that from y equals 0 to y equals 3. Conveniently enough, and not by accident, we have y equals 0, which is just going to make the entire thing 0. So really the only thing we have to do is plug in y equals 3 into that, and we get 3x squared plus 81 over 4. And we got the integral from 0 to 2 of that with respect to x. So integrating that, we get x cubed plus 81/4x evaluated from x equals 0 to x equals 2. We plug in, we get 48.5. And that's all we have to do for a problem like this. That was a bit of a simple example. So a more complicated example, let's take a look at the integral of y e to the xy on the region from 1 to 4 for x and -3 to 5 for y. Now, something I would encourage you to do is try integrating this in both orders and see if one order is easier than the other. So I'm going to go straight to it. And I'm going to say it's easiest to integrate with respect to x first and just take a look at the process on this. So if we take a look at this integral, so we set it up as integrating with respect to x first, meaning that the limits for x go on the inside. So we have 1 to 4 for x, and that goes on the inside with dx. And the limits with respect to y, -3 to 5 for y, go on the outside with dy. So now what we're going to do, because x is part of an inner function, we're actually going to do a u substitution. So we're going to set u equal to xy, since that's what's inside. And if we take the derivative of u with respect to x, we end up with y. And so if u is equal to xy, then du is equal to y dx. So if we write it that way, and if we also then substitute, because if x is 1, then u of 1 is just 1 times y, or y. If x is 4, then u is 4 times y, or 4y. We get that new integral, which is now the integral from -3 to 5 and y to 4y of e to the u du dy, noting that y dx became du. Now, the antiderivative of e to the u is just e to the u, and we are evaluating that from u equals y to u equals 4y, which then gives us the integral from -3 to 5 of e to the 4y minus e to the y dy. And at this point, we integrate that again. We get 1/4 e to the 4y minus e to the y, evaluated from y equals -3 to y equals 5, and we can then substitute, and we get an answer that yes, we could solve, but it would just involve being plugged into a scientific calculator. So that is all. That's a quick introduction to double integrals. Please email me with any questions, and I will see you all on Wednesday.